Welcome to Daily Papers, the podcast where we break down the latest research into bite-sized, easy-to-digest pieces. Today, we're diving into the minds of AI models like ChatGPT. Have you ever wondered how they seem to get the context of a conversation? If you start telling a story about a river, it knows the bank you're talking about probably isn't the kind with money in it. How does it switch between these different sets of rules?
It's a huge question, and today's paper tackles it by creating a simplified world for an AI to plan. The paper is called Selective Induction Heads: How Transformers Select Causal Structures in Context, by researchers at EPFL in Switzerland.
That's a mouthful, but the idea is actually very clever. They wanted to see how an AI, specifically a transformer model, learns to pick the right rule for a given situation. To do this, they used something called a Markov chain. Let's define that. A Markov chain is just a sequence of things, like letters or words, where the next item in the sequence depends on one of the previous items. It's like a very simple chain reaction. If you have the rule A is always followed by B, then whenever you see an A, you know a B is coming next.
Right, but the researchers made it more interesting. They introduced different rules, which they call lags. A lag of 1 means the next token depends on the token immediately before it. So the token at position 10 depends on the token at position 9.
But a lag of 2 would mean the token at position 10 depends on the one 2 steps back at position 8. So the lag is basically the hidden rule that governs the sequence.
And here's the game they set up for the AI. They would generate a sequence of tokens, but they'd secretly pick a rule to generate it. Maybe it was a lag 1 sequence, or maybe a lag 3 sequence. The AI's job was to look at the sequence so far, figure out the secret rule, and then use that rule to predict the very next token.
It's like being a detective at a crime scene. You see a series of events, and you have to figure out the pattern. Is the culprit acting every single day, which is a lag of 1, or are they acting every 3 days, a lag of 3? To catch them, you first have to figure out their rule.
So how does the transformer do it? The paper reveals a special mechanism inside the model that they've named a selective induction head. To understand what's special about it, we first need to know about a regular induction head.
A regular induction head is a known circuit inside these models that's really good at basic copying. For example, if it sees the pattern cat goes to animal many times, and then later sees the word cat, it will copy the word animal. It's a simple, powerful pattern copier.
But this new discovery, the selective induction head, is much smarter. It doesn't just copy based on a fixed pattern. It first looks at all the evidence in the text, selects the most likely rule that's in play, and then it copies from the correct position based on that winning rule.
And the paper shows this all happens in a beautiful 3-layer process. Let's stick with our detective analogy. The first layer is the evidence gatherer.
Exactly. For every new token that comes in, layer 1 looks back and calculates a score for every single possible rule. It's like the detective finding the clue and saying, okay, this clue gives 5 points to the lag 1 theory, but 10 points to the lag 3 theory. It's gathering tiny bits of evidence for every possibility.
Then comes layer 2, which acts as the scorekeeper. This layer takes all those little scores from all the previous steps and adds them up. It keeps a running tally. So after seeing a long sequence, it might have a big scoreboard that says lag 1 has 50 points, lag 2 has 30 points, and lag 3 has 200 points.
You can see where this is going. Layer 3 is where the final decision is made. This is the selective induction head itself. It looks at that scoreboard, sees that lag 3 has the highest score by far, and declares it the winner.
And once it's picked the winner, it knows exactly what to do. It says, okay, the rule is lag 3. To predict the next token, I just need to look 3 steps back in the sequence and copy whatever was there. And that's what it does. It selectively copies from the right spot.
The most convincing part of this paper is how they proved this was happening. They didn't just observe it, they actually built a 3-layer transformer from scratch. essentially programming it to follow these exact steps: gather evidence, keep score, and then select and copy.
And when they tested their hand-built model, it performed just as well as the model that had learned the task on its own through training. They even looked inside the brains of both models at something called the attention maps, and the patterns were almost identical. They had successfully rever-engineered the AI strategy.
So, why is this so important? It's not just about predicting letters in a sequence. This gives us a really clear insight into how AI models can be so flexible. They aren't just following one rigid program. They're constantly looking at the context, weighing evidence, and choosing the best strategy from a whole toolkit of rules they've learned.
This paper lifts the lid on that process. It shows us a concrete algorithm that the model learns for selecting the right tool for the job in context. It's a key step towards understanding these powerful models and moving them from being mysterious black boxes to something we can interpret and trust.
It's a fantastic piece of work that helps explain how transformers can adapt on the fly, and a great example of how creating a simple, synthetic task can reveal deep truths about how these complex systems work.
That's all the time we have for today. Thanks for tuning in to Daily Papers.